Welcome back to the workshop. We want to take a look at another example of evaluating a limit at a real number. And in this case, we want to take a look at the limit as x approaches 2 of x squared plus 4 over x minus 2. Once we find what the limiting value is, we want to also prove our conclusion. So in this case, when we plug in x is equal to 2, we will get division by 0 in the denominator. And we want to think to ourselves, well, what sort of a situation are we going to run into? As we get close to values of 2, is it going to go off to infinity on one side and down to negative infinity on the other, in which case the limit would not exist at all? Or do we have, in fact, that it goes off to infinity or to negative infinity? Or do we have a very convenient situation of a cancellation of factors in the numerator and denominator, giving us just a hole in the graph? In this case, since we have x squared plus 4 in the numerator, that's positive, and x minus 2 squared, that's positive, everything is positive. So we know it's going to go up, or that it's going to be above the x-axis. So it's not going to mismatch in infinite limits. Now here, we also have the numerator does not factor, so there could be no cancellation of factors with numerator and denominator, no common factors. So we don't have the convenient situation of cancellation. We don't have the does not exist situation of mismatch characteristics of the graph. So in this case, since it's above the x-axis, we would say that the limit is positive infinity. Right? We're going to show that it goes off to positive infinity when x approaches 2. And to do this, let's begin with some scratch work. And what our scratch work should include is a kind of a description of what we want to do and then the basic work to get us there. So we want to show, so for epsilon, not epsilon here, we're trying to show it to infinity. So for k greater than 0, some large number, we want to find delta greater than 0 such that whenever we have that x minus 2 is less than delta, we have that the function value f of x is greater than k. So we want to find an appropriate value for delta based on a given value for k. And now when I say given value, I mean it's going to be k. We don't choose 10, we don't choose 20, we don't choose 100, a million, or a billion. We simply leave it as k, so that way it's arbitrary. So we want this. We want to show that it's greater than k. So I'm going to take my x squared plus 4 divided by x minus 2 quantity squared. And I want to write it in terms of the absolute value of x minus 2 because I'm working within some window of 2, delta window. I have this expression of x minus 2, absolute value of x minus 2 is less than delta. And I want to find the delta in terms of k to give me this inequality. So I need to have this thing written in terms of the absolute value of x minus 2. So the first thing to notice is that I can't actually just replace this with the absolute value. So I have x squared plus 4 divided by the absolute value of x minus 2 squared. Excellent. Because when I square a value, it's going to be positive. So it doesn't matter what this looked like, it's going to be positive. Those denominators are equal. And then I also want to find an upper bound. For the numerator. And what we want to recognize is that when we're looking at a particular window, particular delta, close to 2, we can look at unlimited values of x. So if delta is equal to 1, then of course we're looking at x values between 1 and 3, which gives us way to limit what the numerator is. So we want to find, oh, and actually, my apologies, we don't want to find an upper bound, we want to find a lower bound, because we want to find that this expression is less than or equal to something. So we want to find a lower bound. This thing is greater than or equal to. Several mistakes there. We want to find a lower bound. So once I find the lower bound, then I know this thing will always be bigger than the lower bound. The numerator will always be bigger, so our fraction will always be bigger. So if I look at our numerator and look at the smallest possible value for x, or the smallest possible value for the numerator, I'm going to get that occurs when x is equal to 1. Whatever technique you'd like to use there would be perfectly fine. So we have that x squared plus 4 is always going to be greater than 5. Right? Plug in 1, you're going to get 1 squared plus 4 is 5, but our x values are greater than 1. So we have that it's greater than 5. So this gives us that the expression is greater than, this is greater than 5 over the absolute value of x minus 2 squared. So now I have it in terms of x minus 2, or the absolute value of x minus 2. So that's fantastic. I want this to be equal to 5 over delta squared. Okay. In fact, this will be greater than, because delta is smaller than delta is greater than x minus 2. So when I divide by a larger number, I end up with a smaller fraction, and I want this to be equal to k. So that way I have this expression, the function value, is larger than k. So I want to solve this guy right here. Take a look at this. Okay. Multiply both sides by delta squared to get 5 is equal to k times delta squared. And then divide by k to get 5 over k is equal to delta squared. And then square root each side to find that delta is equal to the square root of 5 divided by k. So I have two options for delta. I want delta equal to 1, or I want delta equal to the square root of 5 over k. And those are the values that I will use in my proof. So let's erase the scratch work. And then move on to the proof. So let's let k be some number that's greater than 0, and we want to choose delta to be equal to the minimum of 1 or the square root of 5 divided by k. This will allow us to give the function less than or equal to k after several manipulations. So for x minus 2 less than delta, we have the function x squared plus 4 divided by x minus 2 squared is strictly greater than 5 divided by the absolute value of x minus 2 squared. And this is because we have that delta is less than or equal to 1. And we have that this is greater than 5 divided by the square root of 5 divided by k squared, because delta is less than or equal to the square root of 5 divided by k. And this is equal to k. You're welcome to include the manipulations that get you there. Thus, the limit as x goes to 2 of x squared plus 4 divided by x minus 2 squared is in fact positive infinity. That's what we wanted to show, so we should indicate the end of our proof. Again, indicating the beginning and the end. All right, so that is using the definition to prove that we have an infinite limit. Another example will be coming to you guys shortly. We'll see you soon.